Welcome back. Oh, I'm blind. So, but it doesn't matter if I'm blind. We will hear Kenny Gryp, and he will speak about troubleshooting with sowie MySQL problems quickly. So,
okay.
I know he had how many? 94 slides?
94 slides, yes.
So, troubleshooting problems quickly, also slides quickly. Enjoy.
So good morning. So I'm going to try to have more slides than Maciek later on today. So he said he had 91, so I had 94, so that's good. Okay, so I'm going to talk about expert troubleshooting and the way we troubleshoot a lot of MySQL problems when we do some consulting at Percona. So this is a little bit the chapters that I'll talk about. First, the problem, instrumentation, and then I'll have 3 different kinds of troubleshooting. There are more types, but I'm going to show you how to have more insight in troubleshooting a specific query and optimizing it, then global performance problems, and then intermittent performance problems, which are the ones that are most hard to get. Okay, so the problem. So when you have a problem, you need to think again and think, what is the real problem? I can give you some example of something I recently had with some friends, some discussion. It's not about MySQL, it's about Tomcat or some web server. So I had a friend and he said, Tomcat is behaving weird. Tomcat is stalling. So I told him, okay, I can help you or I can try to help you. So what really is the problem here? So he says, yeah, connection pooling, networking, something. Okay, no problem. So what is the problem? I don't know, I'm looking for it. Okay, that's not really the problem. So I went on in the discussion and they got really mad at me because I was keeping on asking, so what's the real problem that you're having here? So a little bit later on they said, like another person said, like, okay, networking, it's probably networking, so I can see 82 close weight states by looking at netstat. Okay, so another guy comes in and he says, okay, we can change the timeout for the fin weight to 20 seconds instead of the default of 60 or 180, I don't know. So they were just guessing and trying to optimize something or fixing some problem that they don't even know what the problem is. So I kept on laughing because time wait, that's like the typical thing people do is reduce that timeout, but I've never seen it actually solve anything. So they went on and I really kept on asking, so what's the real problem here? So they said it's a problem with the Tomcat connection pool, connections stay open. So I tried to rephrase myself and say, hey, how do you know that it is Tomcat? What do you see? So there's nothing in the error log they mentioned. Well, for me, there's no problem then. They had no data to prove that this is the problem. So after a half a day, the guy ended his job and he called me in his car and then he really said, okay, the login pages keep on loading. So finally, after like 6 hours, we have the problem. So really, what is the problem that the business or the application is facing? So I see that a lot when working. A lot of times when actually explaining the problem, they're mentioning some kind of behavior. Maybe a cause, maybe the effect. And most of the times it's just the effect that they think is the problem. So what I want to make sure is that you really need to step back, think about what is really the problem here. So don't look at some random thing. Don't think that it will probably be Tomcat. Oh, in the end, it actually turned out to be the database. So I don't know. They spend the whole day optimizing. So that's kind of bad for them. So don't limit yourself in where you're looking. If you say that Tomcat is the problem, then you're only looking at Tomcat. While in fact it was just slow login, which could actually be anything. So don't ever trust anybody. That's something I learned. If a customer says something or if a colleague says something, don't trust them. Don't trust yourself. Don't trust anybody. So always try to look at data try to figure out, what do I see, what metrics, look at your instrumentation. Guessing is something you might be able to do, but you're actually lying a little bit to yourself, and you might actually cause, like in this example where Tomcat was not the problem, a lot of waste of time. So, the problem, sorry, I had to start with that. It's not really how to troubleshoot, but it's the start. You need to figure it out. So, instrumentation. So, we know what the problem is now. The second thing is actually we should measure. So, we should start measuring like a boss, like that woman here. She actually measures stuff. What is measuring? So, I'm at 10% now, so I hope I'm on track. So, measuring, instrumentation. So, it is actually, we do measurement. Some quote here from Tom DeMarco, I don't know who that is, but he says you can't control what you can't measure. So you cannot really troubleshoot anything, you cannot really optimize anything if you don't have any data to look into, to see if it actually solved it or not. So for example, with a car, you have some basic information in cars. How fast is it going? How far is the car going? How am I consuming fuel? Do I need oil or not? So everything should have instrumentation. So one example here, so why do we need to instrument? In this example, and this is, it's not related to the example that I gave of Tomcat, but it turned out to be the same problem. So imagine you have a bunch of web servers and a database, in this case MySQL. And a login takes about 15 seconds. Well, what is the problem? And in most cases people will say, and guess, excuse me? Reverse DNS. Yeah, in Chris's case, he would say DNS, but he'll be wrong in sometimes. It's not always right. But here we always assume that MySQL is the problem. You know? So that's a guess. So why would people guess MySQL is the problem? Well, there are more than one web server, so I don't see why it would be the web server. So that's some examples that people would give as explanation. So if it's a database and you guess it's a database, it's probably going to be true, but you're lying again, you're guessing again, you're not honest to yourself. So because of that, so the reason why you would think that there are more challenges on a database than on a web server, this seems more simple than a database, so that's one of the reasons. So you're guessing, but you're using your experience. You're thinking, okay, I had this in the past, so I'll have a look there first. So that's good, that you guess and look at the database first. But you should try to see if your guess is actually good. You should prove, is that guess that I'm making actually a good one? Also, the proving part, here it's mentioned as it's a lot more important than knowing. Well, proving actually is kind of motivating. If I do some troubleshooting and I guessed and I solved the problem by guessing, I don't feel so good. You know, it's much better if I have data. I can see what is happening before I'm troubleshooting something. I say, let's change that setting or do that optimization, and then it's resolved. And you can actually see data where you can see that the problem is fixed. I am more happy. So, how do we instrument, or how do we measure? And one of the things that we can do is we should use a sequence diagram to actually see the flow of information in each of the components of my applications. So here is an example. So the logging example, the browser does a submit to the web server. Some CPU is spent here, or some actions are done here. Then the user is checked if it exists on the database. The result is returned. Then what happens is the last login date is being updated. And you can see this is the amount of time that it takes, is that updating the last login date takes the most time. So if you have information like this in your application, if you can make sequence diagrams like this or get similar data out of it, you actually have more data to see, okay, last login date, updating that field, it takes most time. Okay, so why are we spending a lot of time on that? So we already narrowed down the problem. We know we don't need to look at the web server, it is the database somehow. Okay, so let's do some analysis. So here, this is the update that happens. We update the users table. We set the last login date to now, where primary key, so the user ID, is n. Okay, so it's a pretty simple schema. So there's a lot of columns in here, and then the end one is last login date, date time. So what do we do to troubleshoot? We can, when that problem is happening, the slow login is happening, we can actually do show process list on the database. So what we see here is, and this is indeed a very simple example, we found that something is happening with the updates, and one of them is updating, and all the other ones are locked. Okay, so you know there's something wrong with the update. So maybe if you look at uptime, so if you look at uptime, you see the load average. You can see it really doesn't come with load, this problem. So if you look at CPU, in that case, it doesn't really give you any clue if the database is a problem or not. So it is okay and it is necessary to actually monitor CPU, memory, usage, and everything. That's really helpful. But in this case, it doesn't say this is the database is the problem here. Even if you look at the slow queries, you could see that slow queries is still 3. So value is not increasing, even though the long query time, so the time it has to take a query before it is written to the slow query log, is set to 1 second. Even if they take longer, they are not written to the slow query log. Reason for this is that log time does not count towards that long query time. So it is not logged to the slow query log. So some problems come without load. So you need to look into have that application data. So guessing, again, try to prove your guess. Don't trust it. Try to find out how do I normally troubleshoot. So guessing is bypassing, but try to really prove it with data. So here are some concepts about load, utilization, scalability. So load is how much work is actually coming in. How big is the backlog of my database, for example? So utilization is how much of the resources are used on my system. Scalability is what is the relationship between the utilization and R. R means response time here. Throughput, and that's what a lot of people think about, and I see a typo in here. How many tasks can be done per unit of time? So that's X, throughput. Many people look at throughput as a performance indicator, but that's not true. Concurrency, how many tasks can we do at once? I did a find replace of something, so sorry. Capacity is how big can we set the throughput without making other things unacceptable, like, for example, response time. So the more throughput we send, the more data or the more load we send to it, the higher the response time will become. So there's a balance that you need to find here. So important is response time is the time it takes to do one task. Throughput is how many tasks can I do in a certain amount of time. So throughput is not equals to the performance of the system. So it is actually a relationship between all of them, throughput, utilization, response time, and capacity. Note that response time also includes queuing. So queuing may and will occur in the database. So the service time and the wait time is the actual response time of the task. So what can we do in the database to actually measure and have good instrumentation? So we can look at the error log. This is just for errors. It's not really measuring any load or metrics, but it sometimes gives you an indication. Global status is a really interesting one, and I'll go a little bit more in detail and show you some examples later on. Show engine InnoDB status has some metrics that are not in show global status. So you also need to include that one. Operating system metrics, hardware metrics, load, I/O usage, all those things you should measure. And also the one, like in the sequence diagram, you should measure your response time in your application. Well, how many time was spent in my application? How much time was spent in my web server? One example of that performance in your application is an example here of a table. which contains some information. It's a website, boardreader.com. So we have some page here. That was the page that was requested. So you can see this is the wall clock time. It's 242 milliseconds. And you can see where the time was spent in MySQL. It's only 4 milliseconds. Sphinx, so a full text search, it was 83 milliseconds. So you can see, based on that, where I need to do my optimization if the response time is bad for a certain page or a certain type of pages. So there's a page type here, search, so we can easily get some statistics out of it. So you have account queries, how much time MySQL query was sent. The amount of queries could also be an indicator of increased response time, because it's always sending data queries to the database. This example, or instrumentation for PHP, is an example that can be used to get the same data. So it's an open source product for PHP. You can just put you have to change your application to use the class here, but you can easily transform this. So what happens in this case, it will write Apache logs, special Apache logs that contain that information as mentioned here. And then you can have some cron jobs that actually load the data into the database. If you would send it to the database immediately, you're creating a bottleneck on your own here. So trending is also very important. If a problem occurs, the first thing you should do is look at your graphs and find out what's the difference. Is there any behavior difference compared to what before that the problem happened? And one example is the cacti graphs. It's part of the Percona monitoring plugins, so you can just freely download it. There are many variants on this, but those graphs for cacti contain a lot of MySQL graphs. I think it's about 100 or something like that, maybe a little bit less, but there's a lot of them. A lot of internal MySQL counters are being graphed here. So there are some variants with the similar graphs from Unin, Ganglia, whatever monitoring solution you have. Excuse me? Graphite? Oh, okay. I'm not into that monitoring thing yet. Another thing you can use, so the example that I had here with this is that it's not open source, but New Relic is an APM that actually hooks up to your application. It supports PHP, Java, other languages. It just hooks up and it immediately sends data to the New Relic servers, and you get data, information about response times, about your application, similar to the ones mentioned in this table. And in many cases, applications write their own implementation of that instrumentation. Okay, so now about really troubleshooting some problems. So for a slow query, these are things that I would recommend to do. People know explain, I guess, I hope. If you're optimizing a query, you do explain of the select, and you see is it optimal or not. It's limited. It shows you good information, but there's more that you can use to actually have more, have more data out of it, more information out of it. So we have show session status, show profiles, and some extended statistics. I'll show you briefly. So this is select. So we explain it, and this is the explain output we get. So what we can see is that table cast info is used first, the key person ID is used, and it will approximately read 8 rows. It will create temporary file table and use file sort. So sorting has to happen. The second thing, so for every matching row here, it will actually do a join with the title and look up data in the title table, and it will also use the primary key here. So this is an estimate rows. So this is not really the amount of rows that it will read. So you can say that 8 times 1 is the amount of rows that it would read. But in fact, it's not really true. And in this case, I'm actually giving a good example because it's a bug in MySQL. If you look at the session status, you actually can see that it does much more than that. So what do you do to get information? So you flush the session status, so all your session counters are being set to 0. You run that query, not the explain, so you run the select, and then you do show status like HA. You can show more, there's like more, but I'll show you the handler statistics. So the handler statistics is actually, the handler is an API between the MySQL core and the storage engine. So every time MySQL wants to read a row, it will go through that handler interface and it will ask, give me that row, or do that for me. So you can have counters there that see how much times a row was requested or an index read was requested. So what we see here is that one time it did handler read first. So this means the number of times the first entry in an index was read. So it says, go to the beginning of the index and give me the first entry. Handler read next, I'll show you, is about 14 million. So this means read the next index entry. So this happened 14 million times. What you can also see is handler read key is 13 million, which means read a certain index entry for me. So 13 million times. And what we have here is handler read R&D next, which means it's 2.4 million. It is read the next row, so not an index entry. So what we see here is that it does not do what we saw here in the explain. It does much more. So it's just a small bug in the optimizer that gave the wrong output. It doesn't usually happen, but it can happen. So this will give you that insight. Another interesting fact is that we have handler write here. So it's also 2.4 million. So it seems to match with this. So what happens is that that temporary table that was actually mentioned here, we know that when we do the select, we write 2.4 million rows. So this means the temporary table was 2.4 million. And the temporary table was then used for the group by. So everything was read from the temporary table. So here you can try to understand a little bit more what did MySQL actually do. So explain is what would MySQL do or what will MySQL do, but the session status showed you what it actually did. Profiling is the next one. This is how you do it. You set profiling equals 1, and then every query you run, profiling information will be stored. So when you type show profiles, you see by default the last 15 queries. So in this case it was this select, and it took 200 seconds. What you can do then is type show profile for query 1. So you see query ID 1, that's the number you want, and then you see the profiling information. So I don't commonly use it, some of my colleagues do, but I don't find it always that interesting. It's only in some cases that it is interesting. But here you can see where in which state MySQL was and how much time it took. So we can see for 113 seconds it was copying to a temporary table. We were copying a temporary table on disk, so disk table was created. The other numbers are really low. And important to know is not every state means what it says. So freeing items or might actually, what does freeing items mean? What will you do if that is high? It's very hard to know. So it doesn't really give you the solution here. Oh, freeing items is how I will set, it's high, so I'll set some setting so it will be lower. No. So you really need to look into the code to be exactly sure. So I have to go to development and ask. They know better. So profiling. So might be interesting in some cases. The next one is a slow log statistics. So this is not part of a normal MySQL server or the MySQL enterprise or community, but it is part of Percona server and also part of MariaDB. We can set the long query time to 0, which means I will log every query to the slow log. And we can set the log slow verbosity to full. And by default, you would only get this top information in the slow log with standard MySQL. But with Percona server and MariaDB, you actually get a lot more information. So it is actually the same information that you would get out of the session status, but it is logged to a file now. So you can actually get some statistics out of it. So you can see how many read operations it did, if there was any locking, transaction locking, temporary table, how big was the temporary table, all that information, like this here, is stored in there. You can also include the profiling information if you enabled it in the log slow verbosity. So it's originally created by Magic, I guess, right? You made this? Okay. Kudos. Okay, so that was an individual query. Now to global performance problems. I'll give you some example. 95% of the response time went from 40 milliseconds to 200 milliseconds. That's a problem. So in most cases, response time is the most important thing in most applications. If it's a website, you want it to respond fast. I don't see a spike in a graph that gives you a text message at 1 a.m. in the morning. I don't see that as a problem. It might happen, but as long as response time is good and no errors are happening, I guess people would be fine, you know, and I don't need to wake up. So I worked at some companies as a system engineer and had on-call service. And if you receive 300 text messages a night, you don't respond to it anymore. So that happens. Okay, so when you have global performance problems, so that instrumentation becomes important now. And first thing, I mentioned it, what you do is you go to trending, like the graphs, and see what is going on. If you don't have those graphs, or you need more granular output, more detail, there's some other statistics that you can collect. And I'll show you some examples, some tools that you can use to get that data out of it. So these are some of the tools. Most people probably know IOstat, MPstat, VMstat. It shows you IO statistics, CPU statistics, and so on. These are part of Percona Toolkit, and I'll show you some of them, how to use them and what they actually do. But first, look at the graphs. I'll quickly go over it. So what we have here is we've got connections. What do we see? What happened? You can see connections has a small spike here. Does that mean anything? I don't know. I mean, look at it. Try to correlate it to your problem. Replication, you can see slave is running, but it is lagging at some times, actually permanently. Temporary objects. So these are some of the graphs that are available in most monitoring solutions. Here you see that the database was restarted. So the buffer pool was empty and it was filled again. So checkpointing, I'll not go into detail here. It's not really showing a problem. This is part of Percona server and it shows you the query response time. I personally think that this is an interesting one because this is the count, this is the total sum of the response times from queries that took 1 microsecond, 1 to 1 millisecond, 1 millisecond to 10 milliseconds, 10 milliseconds to 100 milliseconds, 100 milliseconds to a second. So you can see how the response time is on average for my queries. And if it's a bad graph, it's a bad example, but if you look at over time, you might see that everything shifts down. So this means I'm sending maybe more throughput, so my database is becoming slower. So this graph might show that. This is the count, this is the amount of queries of a certain time. So you can see there was a spike here in green or orange. So this is here. So it's 10 to 100 milliseconds and 100 milliseconds to a second, for example. Anyway, what's okay? PTMext. So PTMext is actually show global status, but it takes it from MySQL admin ext, so that just displays show global status. Shows it every 10 seconds for 3 times. So what we have here is have all those statistics, and PTMext will actually arrange it in columns, and it will show you the absolute value of the first time it was shown, and then the difference the next time it was taken 10 seconds later. So here we see what is actually going on in my database. I can see in 10 seconds I had 1,518 inserts. 10 seconds later it was like 3,200. So when you have some performance problems, you can look at all those things and try to understand what is going on and how is it different when the problem does not happen. So the same happened here with the handler. statistics, they are very low for 10 seconds. This just means like 3,492 times a certain key was read, so a certain index entry was read. So that's really, really low. So this was mainly an idle server. So you've got more information. Another example, query cache statistics, threads, and then you can see the uptime is increasing 10 seconds at each time. So just to show. So there's much more, everything from show global variables in there. So it looks at current behavior of the database, and it will tell you, give you some information, or might give you some information. Maybe I need to do query optimization, because I do a lot of sorting. Handler read and the next is big, so I need to go do query optimization. I do a lot of temp tables, so I need to try to figure out how much temp tables am I creating here. Maybe InnoDB is flushing too much, causing everything to stall or slow down. So PTMax. I've seen some tools that just look at show global variables, show global status, and give you optimizations. It says like, okay, handler read R&D next over the last 10 months, so divided by 10 months is very big. So I would recommend to change this setting to this. It is not a good indication because it's stretched out since the uptime of the server. So that's why looking at a certain time interval, like here, is much better to see what is actually going on now. What is happening now? Next thing, disk subsystem. So most people know IOstat, and it gives you I/O statistics. So this is the amount of reads, the amount of writes that are happening on the devices. So here we see 338 writes per second. Important information that I think is very important is the average wait and the service time. So the actual response time, or the average response time of reads and writes, is the combination or the sum of 420 plus 2 milliseconds. So 422 milliseconds is the average I/O request the average length of an I/O request. So that's a lot. That's really slow. Ideally, you want this to be much, much lower. Utilization is at 100% here, and very important to know here, this is just how many percent of the time was there at least one I/O request. So most databases have a disk subsystem with more than one spindle, or maybe they have an SSD, or they have a RAID 10, or whatever, there's a SAN beneath. So this does not show that your disk is saturated. This just means that at any time during that calculation there was an I/O request busy. It doesn't show you how much requests are going. So don't focus too much on utilization. So response time plus service time. So the problem here in this current IOstat output is that it shows you the response time for writes and reads combined. So it doesn't show you how fast were my writes and reads. And one of the tools that you can use is ptdisktats, and it shows you the same information. It just proc/disktats, and it shows you this information. And I have it over 3 slides. So what we have here is the amount of reads that happened, the average kilobyte of a read request, read concurrency, how many requests were merged, and here we have the read response time. So for reads, the average response time was 4.1 millisecond. So for reads, this is quite good, I would say. The same information is there for writes. So we can see that write response time here is 61 seconds for the 160 write I/O operations we did. So this is a problem. Here you can see disk subsystem is the problem here. I would assume that 61 milliseconds is high. If you have a RAID controller with a cache and you have a battery backup unit, you can enable the write back cache, and this means that the disk subsystem will cache it. And the actual numbers that you can get out of it with the write back cache is 0.1 millisecond. So it's 600 times larger than with a write back cache. Now, if that cache is full and the cache was not able to write all the changes to disk, it's going to be slow again. So you need to buy the appropriate hardware with the appropriate cache and do use the proper disk subsystem for your application load. But 61 milliseconds is really high. With Amazon EBS or whatever storage you use at Amazon, for example, you have a highly unpredictable response time for your requests. And it could be 10 milliseconds, but it could be 1 second even. So it just randomly, if you look at it and you do stress it a lot with random reads and writes, it's unpredictable. So it will affect your response time of your application heavily. So when using Amazon, I would say don't rely on disk too much. Try to keep everything in memory and try to do reads from memory. And don't write too much, for example. So some more information. So how much it was busy, so that's the utilization. And then the total I/O operations per second. So this PT disk stats really interesting. I have an example here on a global performance problem. So what happens? A drop table is being done every night and the database stalls. So database hangs. So we were asked to look at it. So what do? The first thing we do is we look is NODB file per table enabled, which means that every table gets a different table space, a different file, so table name .ibd, and they are using XFS. So that's good, because extended tree and deleting files, so drop table is removing that file, is actually slow. It's really slow. So some benchmark done by Magic in 2009 shows that XFS is much, much more efficient than that. So in this case, the customer, they were using XFS, so it was not related to the file system or anything. So when the drop table was happening, we did a show engine INODB status, and in the semaphore section, you can actually see some kind of things, and I know it's a lot of data. So things that that you need to look at is, you can see that a certain thread, an internal thread in INODB, was waiting at some point in the code, some place in the code for a certain amount of time for some mutex, for some kind of locks. So locks have to happen in the database to ensure something, so only one can do a certain operation at the same time to make sure that, the database performs good. It's maybe a bad example here. So, so what I can show you here is there's something going on with the dictionary. So the INODB dictionary. So this means that, and we know that if INODB does something in the dictionary, like creating a table or updating the dictionary cache, it takes a lock. So it takes a lock, and only one can do it at the same time. So what do we see here is that those locks, other queries are actually waiting for that lock to be freed for 52 seconds. So some query, some thread, some operation in INODB is taking that lock for a long time. So how do we investigate? So we know, okay, it's related to the dictionary. So next thing we can do is, poor man's profiler. So this is a GDB stack trace. So it's PTPMP. And what it does, it just takes a state of all the threads that are running in MySQL, and it shows the count of them. So 66 threads in MySQL were busy doing something like I/O handler, fill I/O wait. I'm not a developer, so I don't know much about it. So 66 threads were doing this. 4 threads were handling some kind of connection. So I removed a lot of the data because it's kind of big. But most of them don't seem to show any clear indication what is wrong. Sometimes it does. And in this example, you can see that buffer invalid table space. It's kind of weird. So you can see delete table. So I just look at like that. I ask Alexi to really look into the code for me. So you can see this doing some operation with dropping that table. So, okay, something is happening in that function that is taking a lock. It might possibly take that lock for a long time. So PTPMP shows you what are my threads doing right now. So just the count of them. The other thing we can do is do O profiling. So we can see in a certain time span, where was CPU time spent? How much % of my time was spent on some certain function in MySQL. So this has shown that 44% of the time, 42% of the time, it was actually doing that buff-LRU invalidate table space. So I used that information, probably went to Alexi, and then it turned out that when you have INODB file per table equals 1, dropping a table removes the table space. So in memory, all the pages that are referring to that table space actually have to be removed from memory. So when it was doing that, it was holding that lock. So if you have 200 gigs of memory, it has to run through all that memory and remove them. So that's why it takes a long time. So there was some fix in Percona server, INODB lazy drop table that optimized it. So here's a blog on how it was diagnosed and solved. So if you enable that, performance is increased. It's also fixed in Community MySQL 5.5.20, although I heard that it's not completely fixed or some weird behavior. Okay, so we did that, and for one customer it resolved the problem. However, we had another customer later on that still had problems. Another thing we can do then is use that PTMex tool. So I showed you some handler statistics, but there's also a lot of INODB statistics in there. And you could see that INODB mem adaptive hash, which is the status variable in Percona server, is how big the adaptive hash index is inside INODB. And you can see that every 10 seconds, or every second in this case, it was reducing a lot. So that was kind of strange. The adaptive hash index was shrinking. So the thing was, the bug fix that was done here actually did not resolve the same removing of the pages of the adaptive index. So this was fixed in 5.5.23, and that's how we troubleshooted and found the problem. So this is rare cases, but it happens, and with those tools you can actually have data to back up what is going on and give information, pass information to development or find out what is going on. A workaround here was to disable the adaptive hash. So that's a possible workaround. Next. So next use case, there's bad performance, response time went up. When we look at PTMex, we see that handler read R&D next is very high. So we see that it is 86 million. So if we took a PTMex with a difference of 10 seconds, it's about 8 million rows, data rows that were reread. So this means, okay, there's a lot of table scans going on, or a big table scan is going on, which actually impacts your performance, or possibly impacts the performance. So what do we do is we can go and have a look at the slow query log, because we enable all the queries, we log them all, and that way we can see how many rows were read, so we can try to identify which query was it. One of the examples here is, and I showed you those extended slow log statistics, is we can have that information, and what we can then do is if the slow log is very big, we can grep through it, we can use some whatever you want to do to analyze it, but there's a tool that actually investigates the slow query log. So it's also part of Percona Toolkit. It's the Percona PT Query Digest. So what it does is generates reports from different input. So we have the slow query log, but it can also parse bin log files, look at show process list all the time. It can actually parse PostgreSQL log files, the general log, but the general log only shows you the query, not how long it took, no statistics about it. But you can also use TCP dump and capture all the network traffic, and PT Query Digest can actually read the protocol and find out the queries that were happening, get some statistics, some response time information out of it. It can do that. It can read the MySQL protocol, the Memcache protocol, and HTTP protocol. So commonly it's used for MySQL, but note that you can do it for other things too. So what does it do? It does grouping and ordering of different settings. So everything that is actually mentioned in here, you can group by, you can filter on it. There's a lot of flexibility that you can do here. I show you some examples. We can say some advanced filtering, give me only selects, give me the ones that do InnoDB read operations, give me the one that were query cache. This is the example output, and I'll just skip this because I have a lot of slides remaining. So by default, it will look at the response time, and will sum all the response times of similar queries. So similar queries is the same query, but with different data values. So this is a select join on table 1, table 9, table 2, 3, and 4. So it was called 12,000 times, and of the total response time of that log file or TCP dump, 62% of the response time is actually caused by this select, by this particular query. And you can see it's ordered by default on the response time. So when you're doing optimization, well, try to optimize this one instead of this one, because this can give you a lot of benefit and give you a lot more resources, again, free up resources. So this shows you this one is the one I need to optimize. So that's only the beginning of that report. The next thing we see is information about query 1. So on the left top, you've got query 1 here, and it was run 17 times per second. So it's just the first query here, query 1. Also important to know is, you can look at which query took longest, but in this case, the response time for an individual query was only 112 milliseconds by average. So this means if you just look at the slow query log, it's not the slowest one, but it's just the total sum, the amount of times that that query was run was actually more than 62%. So it's not always the slowest query that is taking the resources, it's the one that is run most or most frequent that could cause it. Okay, so you just have a lot of information here. I'll show you minimum, maximum, average, 95 percentiles of all that statistics, all that information. So execution time, rows affected. So it can help you try to troubleshoot. The next thing is a query time distribution. So remember that cacti graph I showed you with the query time distribution. This is similar, and it shows you how much of the queries were between 10 and 100 microseconds, and between 100 milliseconds and 1 second. So you can see, in a lot of cases it's very fast, but here it's really slow. So why is that? So if you look at the query, it's a select from some logging table. So give me the user agent Mozilla, for example. So this is the data that is variable. So, so one explanation for this could be that the queries here didn't return any results, but here it did. Or the queries that were run very fast, they were in memory, the data was in memory, and in this case it was not in memory and it had to come from disk. So here you can see how stable that query is. Another thing could be that the data that you select can also highly affect the response time. One example we use in training is if you select from a movie that starts with a Z or with a movie that starts with a T, well, there's a lot of movies starting with the. So there's much more matches there. So it is much slower. So the data you select is also very important. PT Query Digest can actually show you multiple queries, and it can show you the worst queries immediately. So you can see which one which data you selected was actually slowest. Okay, moving on. This is an example by parsing the slow query log from a Percona server, which has that low slog verbosity enabled. So you can see much more information. Sort merging, temp tables were created on disk. InnoDB read operations, how many InnoDB pages did it read? Query cache hit when, how much percent file sorts, things like that. Okay, so I have not much time left. Intermittent performance problems. So we've used those tools, but when you have a problem that is happening randomly, you actually, you can't just sit there and wait to run all your commands. And as example here is you can't collect or observe 45 things at the same time if it happens. So there are some tools that enable you to collect data, to stalk some condition and then collect data. So it's called PT stalk. And PT sift is another tool that will help. Okay, so there's a problem happening at some random time, and here's an example by using show global status. We show you the amount of queries per second, the amount of connections, and the amount of threads that were running. So how many queries were active at the same time. And you can see that it's pretty stable, 700, 800, 600, and it suddenly drops to 100. So this is wrong. Something changed here. You can also see that there were more threads running at the same time. So this is when we need to collect the data. This is what we need to find out, what is happening in those 3 collections that happened. Another way to see it is by parsing the slow query log, providing that you log all the queries, of course. So you can see that there is a spike, an increase of queries per second, and suddenly a drop again. So this shows you that something is going on at that time. So these examples give you some information on when is it happening and when do I need to trigger. So that's a trigger that we call it. So what is the condition that I see when the problem starts to happen? So you can set, like for example, in this example, we use threads running. We can see that this is increases. So we can configure ptstalk to actually collect data when threads running goes above 15 in this case. So when it goes above 15, automatically data will be collected. This is also the default behavior. So don't set it too low, don't set it too high. Obvious reasons, too low you get false positives, too high and you will not always get it. In most cases, threads running is very good, is the best one. Threads connected sometimes. There are some others that you can create, and you can create your own triggers for it. And I have some examples. So what value should you use? In this case, threads running. So ptstalk collects a lot of data. You can actually collect that GDB, so PTPMP information. It can do the O profiling for you already. It can strace, and it can collect MySQL data, TCP-dump data. These are settings because strace and GDB might in some cases crash your machine, and you don't usually need it. So beware when you use it. That's why it's disabled by default. So the threshold for threads running was 100 in this case. That's just the basic configuration. So it stores the data, it collects the data and stores it in varlib ptstalk. And here's an example of all the data that it collects. Open tables, PMAP, process list, multiple times, PS, stack trace, sysctl values, top output, show global variables, vmstat output overall. So by default, ptstalk collects data for 30 seconds. So what happened in vmstat on average in 30 seconds? And vmstat contains what happens every second or every 10 seconds with it. Disk stats hostname, IODB statuses, multiple of them, IOstat, disk stats, there's a lot of information here. And this is when the trigger happened. So you've got multiple, so this is 2011-07-21, 1140, and this is 1110. So multiple collections actually happened. Now this is a lot of data, so you need to process that. So that's why ptsift is there, if it works. So ptsift of current directory, and these are all the collections that happened. You can then choose one of them, and it will show you some summary of the data. So here's some, how many active transactions were there, some basic vmstat output, the process list, how many queries were in which kind of state. So this gives you an indication. You can then go into an interactive mode and see ptmex, see disk stats, see all the other files that are happening. Okay, I'll have 2 use cases here, 2 examples. So in this case, we have query pileups and high disk I/O at random times. So, okay, we don't know much. We don't know what triggers it yet. So let's just collect ptstalk with threads running larger than 10. So we collect the data. And when we process the data, we actually see in the meminfo, so the write back actually reduces and then grows again. So that's the special thing we saw in there. So write back is actually the file system cache, has a write back cache itself. So you can see that the write back cache of the kernel's file system cache is actually going to 0 and then increases again. So we used threads running at first. So what do we do then is we actually changed ptstalk and actually collect when write back was starting to decrease. So when we collected ptstalk, it collected some data at some times, so here are the times it happened, when the write back hash was reducing. What we noticed was that every time a collection happened, a new binary log was actually created. So they matched the time perfectly here. So, okay, there's something going on with the binary logs. So after some investigation, so you have to know with MyISM and binary logs, they are not flushed to disk by default. So what happens is MySQL writes it, and the file system cache can cache it. It will not write it to disk immediately. Unless you set sync bin log to 1, for example, it will sync all the changes to disk and ensure that it is written to the disk first. If you don't enable that, which is not enabled by default, it will leave it up to the file system, to the kernel to actually write it at some point in time. So when your machine crashes, or when the operating system crashes, you lose data. Your binary logs will most likely be corrupt. So what happened is when the binary log was rotated, the file system cache decided, let's flush those changes and write it to disk. So we saw a high increase of disk writes, but it affected our normal response time and of the other queries. So by default, the file system cache is actually 10% of the total amount of memory. So if you have 200 gigs of memory, 20 gig of it can be file system cache. So you can reduce that and set it to 1%. So it gets smaller, so it starts flushing those changes earlier. The kernel decides to do it earlier. And another thing we did is we reduced the binary log size from 1 gigabyte to 50 megabyte, which just means that it will do more of those flushes and smaller flushes. Instead of writing 1 gigabyte and affecting or overloading disk I/O, we changed it to 50 megabytes. So the spikes were removed by just changing those settings. And I've got 1 minute and a half remaining, and I have one example. Another problem. There's a lot of lock contention inside INODB. The customer has no idea what's going on, and we don't know what caused it. So what we can do is we can use our extended slow logging as in Percona server and see what lock waits there were. So we can see which queries were waited and which queries were waiting on what. It's not always very easy to see it that, but one way we can do it is we can configure ptstalk, write a script that looks at transaction lock waits or looks for long-running transactions and then collect data when it happens. An interesting fact that I did in the past was I captured TCP dump data when it happens. Then we process it with PT query digest, and then we see when the problem happens, what is all the queries that are coming in? What are those transactions doing? So one example here is that we had a transaction that had some locks here and had some changes, and it is active for 14 seconds. So 14 seconds is a lot for a transaction. So other transactions were waiting on this transaction to be committed. No query was run here, so it's kind of hard to see what is going on here. What is that transaction doing? It could be idle. The application could be doing some other request or spend some CPU cycles doing nothing. But you can have the MySQL thread ID and do show full process list and then match the thread ID with an IP and a port. That's one example. But in this case, we captured the TCP dump data, and then we actually looked at that thread ID, that port, and we looked what was that transaction doing afterwards. So it turned out that there was an application bug, and the transaction was stuck in a loop. So it was doing the same queries over and over again, the same writes over and over again, and TCP dump and ptstalk helped us to actually solve that problem. So, summary, find out what the problem is. Don't try to guess, try to prove your guesses. Have instrumentation, have data to back up your troubleshooting. Troubleshoot by using data. Go beyond explain when optimizing individual query. When you have global performance problems, look at some global counters and statistics in that certain period, time span when the problem is happening. Different problems require different tools, of course. For those intermittent performance problems, PT-Stalk has proven to be really effective in nailing it down, collecting the data, and helping you to troubleshoot the next morning. So that was it. Here's some links of the tools that we used. So yeah, any questions? You have -1 minute. You can talk to me afterwards. No questions? Good.
Actually, I do have a question. Yeah.
Okay.
I want to know how the impact of monitoring or debugging is on the live system. And I assume you do this on the live system because of the errors only occur on the workloaded system.
So when does it affect a lot? Well, GDB will stall the database for a while, so don't do GDB by default unless you know that you need it. But most others, they just do procstat sysctl. That doesn't really affect it. Show engine inodb status. It might cause some performance, some small locking, but it's really low and usually doesn't lock it. I would say if you don't do GDB, it's not going to affect much here. No, I'm checking here. No. Yes.
Yoshinori Matsunobu has written a PMP replacement quick stack. Yoshinori Matsunobu has written a PMP replacement quick stack that can possibly make that problem a bit better.
Okay.
That will not stall as long as GDB does that.
So in what does he do it? Because I haven't seen it yet.
He is attaching himself apparently to the core image of the database and then scanning the stack manually.
Okay.
It works a lot better if you have a version of MySQL that does not omit frame counters.
Okay, I will see. Maybe you can change it. I have not seen his blog about it yet. Or is it recent?
It is rather recent, yes. It is about 2 weeks old or so. It was very recently on Planet MySQL.
Okay.
Which generally is a resource to recommend.
Yes. planetmysql.com. Any other questions?
So, thanks to Kenny.